Chemistry, we're on to our last lesson in the kinetics unit, and this is on rate mechanisms. So a rate mechanism is the series of steps that a reaction follows to get from reactants to products. For example, the reaction 2NO plus O2 produces 2NO2 does not happen in one step. The reaction consists of two steps. Step 1 is you take the 2NO is the same as saying NO plus NO. So NO plus NO produces N2O2. In the second step, the N2 plus O2 is combined with the O2 to produce the final product of 2NO2. So N2O2 does not appear in the original reaction, but it appears as a product in step 1 and is consumed as a reactant in step 2. This is called an intermediate. Each of the individual steps in a reaction mechanism is called an elementary step. And you're going to learn an important fact about elementary steps on the next slide. So let's start with this reaction. H2O2 plus 2H plus 2I minus produces I2 plus 2H2O. So it has been experimentally determined that the rate law for the reaction is rate equals K H2O2 concentration times concentration of I minus. So experimentally means you do what we did back in the first lesson. You take the different concentrations, different rates, you hold concentration of some of the reactants constant, figure out what the exponents are, and so forth. So this now with the rate mechanism, this rate mechanism has three elementary steps. Now, before I show them to you, you do not ever have to figure out elementary steps. You're not expected to do that. You're given these elementary steps for a problem, and then you're asked to do some analysis with them. So the first elementary step, and we're going to write the rate law, the first one is H2 plus O2 plus one of the I minuses, because you have two of them, is going to produce HOI plus OH minus, hydroxide. Now you see that the rate over there on the right is K1, so that's the rate constant for step 1, times the concentration of H2O2, concentration of I minus. Now something that applies, this is very important, to elementary steps only, is that you can use the coefficients of the reactants as exponents. We said you couldn't do that before when we were doing our analysis of overall reactions, but for elementary steps you can do it. So the coefficient in front of H2O2 is a 1. So that means the exponent in the rate law above H2O2 is a 1. And the coefficient in front of I minus is also a 1, so the exponent there will be a 1. So you can only do that for elementary reactions, not for the overall reaction up above. In other words, you can't take the 2 in front of the H plus and make it an exponent. So step 2. So what's going to happen here is the OH minus from step 1 is going to go in as a reactant to step 2. Then you're going to take one of the H plus ions, you're going to put those together to create H2O. So the rate for that is going to be K2, that's the rate constant for step 2, times the OH minus concentration raised to the first power, because the coefficient in front of OH minus in that reaction is a 1, times the concentration of H plus raised to the first power, because the coefficient in front of H plus is also a 1. Now we go on to step 3, and we take the HOI out of step 1, plus another one of the H plus ions, plus another one of the I minus ions, and we produce a final product, I2 plus H2O. So just like in Hess's law, you're going to add the H2Os on the right side of the arrows in step 2 and 3 to get 2 H2O. So that would be your final product in the overall reaction. So this is a key point. For an elementary reaction, that's step 1, 2, and 3, you can use the coefficient of the reactants as the exponents in the rate law. Remember, we learned earlier in this unit that you must determine the exponents for the overall reaction experimentally. That's what we did in the very first lesson. But And you would for the overall reaction up at the very top. You would have to do it that way. But when you have elementary steps, you can use the coefficients as exponents. You don't need to understand exactly why that is, but it is true. So continuing with the reaction on the preceding slide, the rate law is rate equals K, concentration H2O2 to the first H2O2 times concentration of I minus. So the rate mechanism has 3 elementary steps, so we've already seen those. We'll bring those up. So let's assume that the first step is the slow step. How do you know that? That's something else you have to be told. You're not expected in any way to be able to figure that out. So let's say the first step is the slow step. So then that means that the rate of the overall reaction up above is going to be the same as the slowest step down below. So if step 1 is the slow step, however fast it goes, that's how fast the overall reaction can go. It can't go any faster than that. So the overall reaction cannot go any faster than its slowest step. That means the rate law for the slowest step is going to be the rate law for the overall reaction. You can see that the rate law of the overall reaction is the same as the rate law of step 1, which is the slow step. This means that the speed of step 1 is limiting the speed of the reactions. So step 1 is the slow step and is called the rate determining step because it determines how fast that reaction can take place. Now we're going to shift gears for a second here and talk about something called molecularity. The molecularity of a reaction refers to the number of molecules that participate as reactants. So unimolecular means 1 reactant molecule, bimolecular 2 reactant molecules. They can be the same compound, but there's 2 different molecules, and termolecular is 3 reactant molecules. So if you look at this table, unimolecular, an example of 1 reactant would be a decomposition reaction. Whatever A is, it's some molecule that's coming apart. So the way you would write the rate law is rate equals K, and since it's elementary reaction, it would be concentration of A to the first power, since over there A has a coefficient of 1. Now A plus A is 2A, so the rate is going to be K concentration of A squared, because the 2A, that coefficient of 2, becomes the exponent. A plus B, rate equals K, concentration A, concentration B. A plus A, that can be represented as 3A, so that's rate equals K, A to the third power. A plus B is going to be A squared, because 2A will produce an exponent of 2. So K, A squared B, and A plus B plus C is going to be rate equals K, A times B times C. So here we see that concept again. So note that A plus A is the same as 2A, so we rewrite the reactions so they appear as follows. A is rate K A raised to the first power. 2A is K A squared. A plus B is K A B. 3A is K A to the third. Coefficient becomes the exponent. 2A plus B becomes K A squared B. And A plus B plus C equals K A times B times C earlier. So you can see that the exponents in the rate laws do equal the coefficients of the reactants. This illustrates the point made earlier. So for elementary reactions, only you can use the coefficient of the reactants as the exponent in the rate laws. Remember, we learned earlier in this unit that you must determine the exponents for the overall reaction experimentally. That's what we did in the first lesson. So compute the rate law for the reaction without using experimental data, but using the rate mechanism shown below for the reaction. So there's the overall reaction. 2N2O produces 2N2 plus O2. So step 1 is going to be N2O is going to produce N2 plus O. So the rate law for that is going to be rate equals K1 N2O to the first power, because the coefficient in front of N2O is 1. So we're going to say that's the slow step. Again, you got to be told that. You're not expected to figure out what the slow step is. Step 2. Now you're going to take the other N2O. In the overall reaction, you have 2 of them. So you're going to take that and mix it with and add it to the O that you got out of step 1 to get N2O2. And so if you use Hess's law, the O's cancel out, and you end up with 2 N2O on the left side. You end up with 2 N2 on the right side of the arrows, and the O2 on the right side of the arrow. And we're going to say that second step is the fast step. So let's think about what that means. It means that as you produce O, it's going to go into the step 2. And it's being produced very slowly. So step 1 is making O very slowly. So as soon as it makes an O, it's going to immediately get gobbled up into step 2, and the reaction is going to continue to the end. Okay, so that's a pretty natural, easy to understand process. O gets made very slowly in step 1, and then it's immediately taken into step 2, a fast step, and it goes to the end. So that's the easy situation. Okay, so there you see the overall reaction down there. So since the first step is a slow step, its products N2 and O immediately become reactants for step 2, and the overall reaction is completed. The rate law for the overall reaction equals the rate law for the slow step, step 1. So you see that that's going to be the case right there, and so there it is. The slow step rate law is K, concentration of N2O to the first power, and that's the overall rate law. A rate mechanism with a slow final step creates a complication shown in this example. Now this is going to be tough to learn at first. You do it by repeating. You learn anything in life by just repeating it enough times. So compute the rate law for the reaction without using experimental data, but using the rate mechanism shown below for the reaction. So the overall reaction is 2NO plus Br2 is going to produce 2NOBr. So step 1, you're going to take one of the NOs, the 2 NOs rather, and write them as NO plus NO. That's going to produce N2O2. And so the rate law for that is rate equals K1 NO squared, because 2NO, the coefficient, becomes the exponent. We're going to say that's the fast step. That's told to you. Now step 2, you take the N2O2 and you add in the Br2, and that's going to produce 2NOBr. And that has the rate law of K2, meaning step 2's rate constant, times concentration of N2O2 to the first power, Br2 to the first power, because these are elementary steps. So you cancel those using Hess's law, principles of Hess's law, and that's the sum down below, and that's what you have up above as your overall reaction. So what that means is that the rate law for this overall reaction is going to be the slow step, which is K2 N2O2 times Br2, which you see as the rate law for the slow step. So the rate law for the overall reaction equals the rate law for the slow step, step 2. We will call this the temporary rate law for the reaction, and you're going to see why it's only temporary. So the rate law for the overall reaction is K times N2O2 to the first power, Br2 to the first power. That's the temporary rate law. But there's a problem. The temporary rate law includes the intermediate N2O2. The final rate law should only include reactants in the final equation, which is NO and Br2. Those are the only reactants in the overall reaction, NO and Br2. So you can't have N2O2 in the rate law when it's not one of the reactants in the overall reaction. So for this reason, we need to find a way to express N2O2 in terms of either NO or Br2 or both. So I'm going to introduce you to a concept of equilibrium. Most reactions can go back and forth. This is going to be the subject of our next unit, by the way. Most reactions can go back and forth. So this reaction you're looking at has a double arrow. It can go from NO plus NO to N2O2, or it can go in the other direction from N2O2 back to NO plus NO. Okay? And we're going to say that that is the fast step. Okay, it's step 1. Now, this is a reversible reaction, which means it can go both ways, so it can be written with two different rate laws, one for the forward and one for the reverse reaction, because it's effectively two reactions put together in one. The forward reaction is what you see up above. It's NO plus NO produces N2O2. So the rate law for that would be rate equals K subscript F, which stands for forward. It's the rate constant for the forward reaction times NO squared, because NO plus NO is 2NO, and so the coefficient becomes the exponent. Now the reverse reaction is going in the other direction. N2O2 produces NO plus NO. So the rate constant for that reverse reaction is going to be called Kr for reverse. So the overall rate law for the reverse reaction is rate equals Kr times concentration N2O2 to the first power. Now if they're in equilibrium, they're moving back and forth at the same speed, then the rates of those two will be the same. That's what we call equilibrium. It's balanced. It's moving backwards and forwards at the same rate. That means you can equate those two equations right there, those two rate laws. So let's see how that happens here. We can now solve the equation for N2O2. So equilibrium rates means that the rate of the forward reaction and the rate of the reverse reaction are the same. So Kf NO squared equals Kr N2O2. And so now we can solve for N2O2. So how do you do that? You see the equation down below there. So you divide both sides by Kr, you cancel, and now you have N2O2, the concentration, equals the forward rate constant over the reverse rate constant times NO2 squared. So now you're able to substitute out N2O2, which is not in the overall reaction, for something that is, which is NO. We can substitute now the concentration of N2O2, which cannot be in our final rate law, for what we said it was equal to, K forward over K reversed times the concentration of NO squared. So it's going to look like this. There's the temporary rate law. We're going to take that, the N2O2, and we're going to substitute that out for this, the Kf over Kr NO squared. Just a straight substitution. So now you have all these K's over there, KT, KF, KR. Well, you can multiply KT times KF divided by KR and combine them into a single constant. Remember, they're all just constant numbers. So you can combine them into a single rate constant, which will be our final rate constant for our overall reaction. So the three rate constants, KT, KF, KR, are all constants, so they can combine to form the final rate constant, K. So the final rate law includes the reactants for the overall reaction only. NO and Br2, those are the only reactants in the overall reaction, so that's our final rate constant, rate law, excuse me. Rate equals K, NO squared, Br2. Now, catalyst. Talk quickly about catalyst. A catalyst speeds up a chemical reaction without being part of the reaction. A homogeneous catalyst exists in the same phase as the reactant. So it's liquid, liquid, solid, solid. It's the same phase. For a catalyst to work, it must do at least one of the following: increase the number of collisions of the reactant molecule, or lower the activation energy for the reaction, EA. So if we look over there, we see a potential energy diagram for a reaction, and you can see the green line is without a catalyst, and you can see the activation energy is high. It goes up very high. When you put the catalyst in, it lowers the activation energy down. That's the purple line. You end up with the same energy level at the beginning, at the end. It does not change anything about what you start with or what you end with. It just makes the reaction go faster, and so that's the purple line. Because the reactants don't have to climb such a high energy hill, they're going to be converted to products faster. So the reaction pathway shows the activation energy, the highest point on the curve, is lowered in the presence of a catalyst. The beginning and ending energy levels are not changed. All right, so that takes care of this lesson and this unit. It's going to take a little practice to get the rate mechanisms down, but with practice you will become very good at those.